Perfect. Hi, everyone. Good afternoon. I'm very glad to participate in this course/conference on AI ethics. The goal of the presentation is twofold, really. First, to demystify what is artificial intelligence for those of you who are less familiar with it. This will be quite a short part, so maybe 15 minutes. And then we'll focus on this field of AI ethics and what is at stake in this field, and then delve a little bit more into the main concepts we manipulate in this field. So we'll have a first session today of 2 hours, starting now, and we'll have another session of 1 hour and a half tomorrow. So first part, what is artificial intelligence? Basically, we can think of two main types of artificial intelligence systems. First, we have the historical type, which is the symbolic artificial intelligence, sometimes referred to as good old-fashioned artificial intelligence, GOFAI acronym. And basically, it corresponds to the expert systems that were developed in the 20th century, in the 50s and 60s. And they are basically based on facts, rules, and inference engines. And they help encapsulate expert knowledge into, well, these symbolic systems, and they are very useful for many decision systems. And then there is the other part of artificial intelligence, which is referred to often as sub-symbolic AI. Sub-symbolic in the sense that representation of knowledge is not as explicit as in symbolic AI, because in symbolic AI, well, rules are quite an explicit representation of the knowledge of the expert, whereas in sub-symbolic AI, this representation is far less abstract, far more abstract. So there are various types of sub-symbolic AI. One of the most famous ones, and that we will be concerned with in this course, is machine learning. But it's not the only type. There are other types like genetic algorithms, which help explore solution spaces and optimize the found solution. There are some fuzzy control systems based on fuzzy logics. And there is another part of some symbolic AI which does not correspond to this soft computing part at all, which is called nouvelle AI, and which is quite present in the robotics field, and for which the entanglement between intelligence and body is a very strong philosophical assumption. So they take the assumption that truly intelligent behavior can only be acquired through a body in interaction with the environment. And this can be justifiable in the sense that all other types of AI that are only based on software have a philosophical premise that mind or intelligence, etc., is something that is separate from body, matter, etc. So it has a certain philosophical hypothesis. We can make a different one, as is the case for nouvelle AI. And I prefer to set the stage primarily for what is artificial intelligence, because when speaking about AI ethics, one can refer to any of these subfields of AI, and we will be focusing on one of these fields, which corresponds to machine learning, which is the field for which most of the successes we witnessed in recent years are due. So basically, you probably heard about an artificial intelligence beating the world champion in the AlphaGo game. You probably saw some deepfakes where we are able to replace faces either in images or in videos and well, fake some discourses or etc. You probably heard about the Tesla autonomous driving system, or maybe about the deep learning dreams, which correspond to a way of creating feedback loops in neural networks that transform images and make them look as we might sometimes have some dreams. So basically, all these recent successes are due to machine learning systems. And the most prevalent use of artificial intelligence in companies today is vast majority the use of machine learning systems. Of course, there is a big chunk of expert systems in airplanes, in metro systems, underground systems, etc. But now the most modern uses of artificial intelligence are related to machine learning. So when speaking about machine learning, the idea is to explain a little bit what do we mean by that. So it's a branch of artificial intelligence which builds systems that learn from historical data. These systems are not explicitly programmed for the tasks that are being performed. For example, if you want to build an autonomous driving system based on machine learning, you do not encapsulate in the program all instructions for all scenarios and situations the car will face. You do not have a succession of instructions of go into the front, go to the left, go to the right, or go backwards, taking into account all possible situations. What you do is basically use recordings or videos of someone driving or a car driving, and these will correspond to observations or examples that will be used by algorithms to learn what is the best decision to make depending on the situation in the environment. And this is a very powerful idea in the sense that it can be applied nearly to any problem, either autonomous driving or fraud detection or predictive maintenance for industrial systems, etc. All you need to do is gather data, observations on what happened in the past, and then let algorithms learn all the correlations that are present in this data to help you decide, make new decisions in a new environment. Of course, you always make the hypothesis that this new environment will somehow look like the historical environment. Otherwise, what you learned would not be useful. But it can, of course, be different in some details, but still you will have learned the main features that have strong impact on the decisions to be made. From a historical point of view, machine learning is quite old. It did not start with Facebook or Google. It emerged in the 1950s. The first neural network called the perceptron was published in the 1950s also. And we had maybe 15 or 20 years of very strong development of artificial intelligence systems, mainly the symbolic systems, the expert systems. And one of the drawbacks of this period is that promises were too much promises were made at that period. People thought that maybe in the 80s or 90s we would have artificial intelligence that would interact completely naturally and fluidly in natural language with humans, and this of course never happened. So at the turn of the 80s, 90s, despite a lot of investments in artificial intelligence, results were not as good as expected. So we had to cross what was later named the artificial intelligence winter that lasted 10 to 15 years before the rise again of artificial intelligence at the turn of the year 2000, mainly because of the internet and the availability and the building of big data technologies. So basically, the companies like Google, Yahoo, and then Facebook, Uber, etc., started developing a set of new technologies that allowed them to exploit the mass of data that was generated through the democratization of personal computers and the availability of this new system called the internet. And at the turn of the 2010, artificial intelligence and machine learning systems started to diffuse more largely to other corporations which are not digital natives or artificial intelligence natives. And this, there was a period between 2010 and 2015, mainly based on experimentations in these companies around machine learning systems, proof of concepts, etc. And industrialization problems, meaning how can I transition from proof of concept into a system that is well integrated into my IT infrastructure, into the business workflow of users, etc. This set of problems called industrialization only started to be addressed in 2015, 2016 by most companies. And we are witnessing since maybe 1 year or two, more interest in AI ethics problematics. So the goal here is to first give you an intuition of what is artificial intelligence and then analyze in more detail what is important in AI ethics. Please do not hesitate if you have any questions, etc., to interrupt me. The goal for the session is to be interactive and not for me to speak straight for 2 hours straight. So basically, there are two main types of problems in machine learning. You have the so-called supervised learning problems. So basically you have a target, for example, fraud or client churn or failures, system failures, etc., that you need to predict. So this is the target to predict, and you will use historical data to predict this target. We call this problem supervised in the sense that it is, since you have this target to be predicted, the model will be able to be supervised during his learning on what is the task to be performed precisely. In unsupervised learning, you will use similar historical data, but you have no notion of target. For example, you have data about customers, and you want to find patterns or homogeneous groups of clients. So you will use unsupervised or clustering algorithms to classify these clients into groups, homogeneous groups, without prior knowledge and without any specific target to predict. It's just how can I find structure in the data without specifically this idea of predicting something. So very simply, how does a machine learning algorithm work? So here is an example of a supervised problem. We have observations which correspond to the examples from which our algorithm will learn. So here, for example, we have 5, 6, or 7 examples. We have some features that characterize each observation. So here for the observation Paul, we have as features sex masculine, age 37, and number of children 0. And the same for John, Sarah, Ivan, and Alexandra. And then you have the target variable, which is the variable that we will want to predict in the future. And here, basically, it's did the person subscribe, for example, an insurance contract? Here, the variable 0, the value 0 means that the person did not subscribe, and the value 1 means that the person did subscribe. So here we see that Paul, which has features masculine, age 37, and 0 children, did not subscribe the insurance contract, whereas John did subscribe this contract. And basically, we can characterize the features either as being numerical, like age or number of children, or as categorical, a category like sex, for example. And the target variable can be of 2 types, either a categorical variable like here, you are either a 0 or 1, having 0, 5 has no meaning for the initial variable. You either did subscribe or you did not subscribe. But you can also have a numeric target variable. For example, if we want to predict the revenue of the person, well, revenue can take any value, real value. So here you would consider that the target variable is a numeric one. So it's called a regression problem versus a classification problem if we are considering a categorical variable. Both types, regression and classification, belong to the problem, the supervised category of problems, because you have this target that you want to predict. And so basically what we do is simply to split this historical data of 5 or 6 or 7 examples into 2 sets. One that we will call the training set and one that we will call the test set. So the training set here is composed for roughly of 70% of the observations, and we keep 30% of the examples and observations in the test set. We will use the train set to train the algorithm. So basically the model will learn the correlations that exist between the features such as sex, age, and children, and the target variable, which is did the person subscribe an insurance contract or not. And once the model has learned what is the correlation between subscribing a contract and the features of an individual, we can use this newly learned information to predict in new situations. But before doing so, before using it, for example, on Magdalena, for example, which is a new person, a new individual, we want to assess the performance of our model. We cannot just train it on all the historical data and hope for the best in new situations. That's why we kept on the side this test set of some historical observations for which we have both the features and the value of the target variable, but we never used this test set to train the algorithm. So basically the algorithm knows nothing about Ivan and Alexandra. So once we trained the model on the first set, the train set, we will use it on the test set to produce predictions. So basically we will feed the model the features of Ivan. For example, here we will feed him sex, masculine, age 54, and number of children equals 2. And we will ask him, what is your prediction for this individual? Is it 0 or is it 1? And we will do the same thing for Alexander. We will feed it with the sex, age, and children variables and ask him for a prediction on the subscription or not of an insurance contract. And once we collected all the predictions of the test set, we will compare the predicted values with the actual values. These prediction and actual values can be summarized in a very simple manner, which is called the confusion matrix. So basically, you put the actual values in the first row, the predicted values in the first column, and then you compute. Here we have 740 correct guesses of persons that did subscribe the insurance contract. And we have 149 correct guesses of people that did not subscribe insurance contracts. So the diagonal corresponds to good predictions that corresponded to the actual values of the target variable on the test set. The anti-diagonal, mainly the 230 and 50 value, correspond to wrong predictions. So basically, we made 230 wrong predictions of 0 value, mainly persons that did not subscribe, that were predicted not to subscribe the insurance contract, but which actually did. And inversely for the 50 value. So based on this matrix, we can very easily then assess the performance of our model on this test set. And we make the assumption, if our data is representative, that we will have the same performance for new examples. For example, Magdalena, that for which we will collect data tomorrow or in a week, etc. Here I made a bit of a simplifying assumption. The model generally does not directly predict a 0 or 1. They generally predict a probability, and then you have to choose a threshold. For example, if I have a probability above 0.5, then I predict that the person will subscribe a contract. If I am below this probability, I will predict that the person will not subscribe. And then you attach a prediction 0 or 1, depending on this threshold. But other than this simplifying assumption, basically, you have a good understanding of how machine learning model is trained and is evaluated if you understood this slide. So now if we look at the most basic machine learning algorithm, which is the linear regression, you don't need to use complex technologies or programming languages like Python, etc. You can use just Excel to develop this simple model on data that you might have. So basically we have a set of data points that correspond to the price of a diamond dependent on its mass in carat. And basically the linear regression will try to fit the best line that goes through all these points. And this line will help us predict the price of a diamond depending on its mass. So now if we have a new observation with a diamond of mass 0.25, all that we do is see what is the value of the function related to the linear regression for this value 0.25. And here we will see that, well, probably the best estimate for the price is something around $700. And you can use this line, which corresponds to your model, your best model that goes through all these data points, to estimate the price of any new diamond mass observation. So this is the most basic example of machine learning algorithm. The problem is that we cannot always represent the relation between our features and our target variable. Here the feature was just the mass and the target variable was the price. We cannot always represent the relation as a linear one. And you have other types of algorithms that you can use to capture nonlinear relations between the features and the target variable. An example is the so-called decision trees. So here in this example, we want to predict the humidity level, which corresponds to the feature variable h, and using the wind speed, which corresponds to the feature variable w, to predict the temperature. Here, temperature is a numeric variable, so we have a regression problem here. And basically, what the model will do is try to find correlations between position in the h and w space and the color which corresponds to the temperature. So a decision tree generally resembles what you see here on the right. So basically here, the one possible model would be a tree where you ask, do we have wind speed above 60 kilometers per hour? If yes, then a prediction for temperature is 15 degrees. If no, then you ask another question on humidity, and depending on the answer for humidity, you have different predictions for temperature. This decision tree corresponds in reality to a segmentation in the data space. Basically here, the first question you ask on wind speed, and it corresponds to a split here around the value 60 kilometers per hour. And if you answer yes, if the value of the speed is above this 60 kilometer, you are in this part of the data space. And the prediction 15 degrees simply corresponds to the average temperature in this part of the data space. And then if you are not above 60 kilometers, you are in this part of the data space. And here, yeah, we can, of course, again, just simply take an average temperature as a prediction. But as you can see, we have red and blue points, meaning that we have too much inhomogeneity in this compartment of the data space. That's why the algorithm chooses to further split the data space according to the humidity level variable, so that now we have two compartments for which temperature is more homogeneous. So here you have colder temperatures, and here you have hotter temperatures. Then you simply take the average temperature in this compartment for this prediction, and you take the average temperature here for this prediction here. So basically, what all the decision tree algorithm does is simply split the data space into compartments where the values of observations for the target variable here, the temperature, are homogeneous enough. The number of splits and the variables according to which it does the splits is something encoded in the algorithm. It is optimized by the decision tree algorithm itself, but it's something that is not very complicated to understand. If you read the pseudo algorithm, you can quite easily understand the criteria, and they are basically more or less correspond to how can I minimize the inhomogeneity if I put a split, what is the way to minimize inhomogeneity for the next split. And basically, it is this optimization that chooses the variables and the value for the variable at which the split is being performed. Do you have any questions regarding how these two algorithms work?
Hello, sir. Can you hear me?
Yeah.
Sir, I have a question, sir. In probably third slide, sir. The question is, we have a training data set and testing data set, sir, as you said. And while generating the model, the classifier algorithm through which we can decide the class a particular data will belong to, sir, my question is it depends upon the probability? Because yeah, in this case, if we see while designing a model, for example, subscriber, if for a particular in training data set, if the data set is, let's say, some vague data set, therefore in deciding the model, is it depends upon the probability. For example, if the person Paul is male, his age is 37, and he is a subscriber, means the value is 1. In some data, let's say for example, I have 10 data set, and in 10 data set out of 10, in 3 cases the data is subscriber is 1. In that case, how to design a particular classifier model where the data is little vague, or it's difficult to decide whether it is 1 or 0? This is my question, sir.
If I understand correctly, and do not hesitate to correct my understanding, basically you are asking the problem of representativity of data. If I have a set of observations for which I might have different predictions of subscription, and maybe 2 individuals, Paul and Paul Biss, that have very close features, but different decisions of subscription or not, then globally for the same set of features, I will have a probability of subscription. If this is your question, then you are correct. If I have a set of very similar observations which have different results in terms of subscription, This is why the model will predict a probability, because he will take the average value of the subscription, which will correspond to the probability of subscribing when you have this set of defined features. And then what you want is to have good representativity. If is this probability close to what I will observe when running my model in production in a real life environment? And this is what you need to ensure for your historical data. This is generally done by having good historical depth. For example, if I want to train a churn or subscription model, we know that you need at least 2 years, if not 3 or 4, to have good representativity, because you need to at least cycle through a whole year, and then you would probably need 1 year for training and 1 year for testing. And this is the most basic level. If you want a good statistical robustness, maybe you need 3 years for training and 1 year for testing if you want to ensure temporal coherence. Does this answer your question or not?
Yeah, thank you so much, sir. Thank you so much. I got the answer. Thank you.
If there are any other questions from other participants, please do not hesitate. As I said, basically, you have various types of algorithms that you can use to learn either linear or nonlinear relations between your features and your target variables. But a very important concept to have in mind is that you cannot use any algorithm to learn any type of data. A good example of this is, for example, a situation where you always suffer from what the so-called underfitting. If I use a linear regression or a linear model to fit parabolic data, whatever the parameters of my linear model, mainly the slope and the, I don't remember the English word for it, but the value here at this axis, I will always have a line. So I will never be able to correctly fit a parabola. So this is a situation of underfitting. Your model will never be able to correctly fit the data. You will always have bad performance and no possible generalization of your model. The other problematic situation is the so-called overfitting. So here we have the same data points, but what you did is that you used a model that is very complex and that learned all the details that you had in your training data. And here, of course, you can say that, oh, great, I learned all information I had, but you need to distinguish relevant information for the future and noise. And part of the historical information is simply noise. And all these circumvolutions here correspond to noise. What you want to learn is basically the parabola. This is probably the best estimate of what predictions should look like if you want to generalize for new observations. Because here, if I have a new observations, I don't know if you see my mouse, but here at by the end of the parabola, just below it, well, probably you will have a very bad estimation because you went through all the points and it's not the best way to estimate new observations. So basically, remember that you have two problematic situations, which are underfitting and overfitting, and that the good learning is somewhere in between. And this is a very subtle performance to have. You have to have some experience to know when you are probably going to underfit or when are you going to probably overfit. Finally, to close this section on what is artificial intelligence, the unsupervised learning. Basically, if you remember, I said that unsupervised learning is a situation where you have observations characterized by certain features, but no target to predict. You have no prediction to make, just want to analyze your data, analyze if there is a structure in this data, and group observations according to this structure. So here, for example, we have a data set with two types of features, first one on the axis and the other one here. And we have all these data points. Basically, if you just look at it in 2 dimensions as a function, one of each other, well, you see a lot of data points, but no specific structure. But if you look at it here, you can use a clustering algorithm like k-means or hierarchical clustering or dbScan, etc. There are various types of algorithms to analyze if you can group all the observations into isolated subsets. And here the answer is yes. We can clearly see that there are 3 subsets that we can isolate from each other. that probably correspond to individuals that have similar features. And this will correspond to cluster 1, cluster 2, and cluster 3. You have no clear interpretation necessarily for these clusters. This is a discussion you need to have with business experts or domain experts to identify what is the meaning of the clusters. But at least you have this attachment of individual observations to clusters of other individuals that have closer features to them. There is nothing to predict here. You just want to group individuals into coherent groups. So this is the goal of unsupervised learning category of artificial intelligence. So now that we explained very quickly, I know probably some points might remain obscure, but the idea was simply to demystify what is artificial intelligence. It's nothing really complex. It's just putting information in tables, etc., for supervised learning, and just running algorithms that will map this to a target variable or group individuals into homogeneous groups. Of course, you can imagine more complex algorithms around natural language processing, computer vision, etc. But again, it's just a complexification of the representation of data. Here we had very simple representation, mainly human individuals with certain features, etc., that are very easily interpretable. But if you're doing computer vision, you are simply representing pixel levels of gray and putting them as inputs of a deep learning algorithm. So data representation will evolve and be a little bit more complex, but the ideas will remain the same, basically features, input data, and a target to predict, and an algorithm between the two to learn the patterns. So now if we want to dwell into the field of AI ethics, first question is it really a field? What do we mean by AI ethics? What is so specific about AI that we will need specific ethics for this field? First of all, what do we mean by ethics? Well, a possible definition is that it is a fundamental reflection on a field. Here AI, but generally ethics is a reflection on a field in order to establish norms, limits, and duties. So there are two important parts in this definition. The first one is that it is a fundamental reflection, so there is no limit to questioning. And the second part is that we need to establish norms, limits, and duties. And the important idea here is that we do not have to follow what is or take into account the problems of the current situation, but we need to define what should be. So it's not a good reason to dismiss a duty or a limit that needs to be put on artificial intelligence simply because this is not how things are today, or it is something hard to implement. This is not what ethics is concerned about. What is today is not important. The question is what should be. And the criteria to establish what should be are defined through this fundamental reflection of AI ethics. So examples of what is at stake are here. I chose two examples that you probably heard of. Google's filter bubble, which corresponds to an algorithm that allows to filter research results before being displayed to individuals. And there was an experiment that was performed with 87 people across the US that searched Google at the exact same time, being logged out, so no relation to a potential Google account, and in private browsing mode. So you might think that since we have no individual or personal information being used, they should all get the same results. And of course, they did not. If you typed gun control, for example, you see that, first of all, the order of the links is not the same. The advertised links are not the same, and the order of advertised links related to non-advertised links is not the same. And sometimes the links themselves might have a bias towards more right type political opinions or left type political opinions. So how was this performed? Probably the source of information was based on cookies that you use on your navigator, so you need not to be logged in or use a private mode or use other modes of navigation to give information to Google. And the problem this poses is that this means that the algorithm does not give the same reality to all individuals. Of course, here it's not so problematic, but when you compare this to what happened, for example, in the US in the 2016 election, where people really started living in different realities and not basing themselves on the same fact. And we saw this again in the 2020 election. People will start having diverging realities because they don't have access to the same information, even though they ask the same question. And what is at stake here from the ethical point of view is, should algorithms established by corporate companies, private corporates, define what is the informational reality of citizens? The second example is the Cambridge Analytica scandal that happened during the Brexit and also the American elections. Basically, what you see here is an individual to the right that shared information like name, gender, political opinions, spoken languages, location, etc., which is friends with another person that did not share any particular information. But what the algorithm did was basically to build the net of relations between people and exploited without their consent this network information, who is friend with who. And through the individuals that shared more information than others, they were able to predict what would be the political opinions or beliefs of the individuals that did not share that much information online. And they targeted them with political advertising to influence their vote. So here again, this poses the question of how far can we go in exploiting personal data and algorithms to target people for things like commercial advertising or political advertising without their consent, because people generally, when they saw advertising, they did not know that personal data of theirs or of their network was exploited to establish that they might have this political opinion and we should push to them this video or this content. And this is very problematic in the sense that people might think that this is the whole reality there is, because that's the content that is being pushed to them, whereas this was a selective reality through this algorithm that was based on this personal data. So we see that what is at stake here is really simply the shared reality, political reality, citizen reality, on which many decisions are based. And for now, it is based on massive exploitation of data by private companies without necessarily explicit consent and without necessarily a good understanding of how these algorithms are working and make their decisions. And if you look around, there are many official initiatives around AI and ethics, either public or private initiatives. The first one was by the White House office in 2016, a report to prepare the future of artificial intelligence in the US. For example, in France, there was another report on called the AI for Humanity that was a reflection on the place of AI in society and what should be the national strategy on the development of AI regarding its use cases, on impacts on society, employment, etc. The European Union drafted the guidelines of what a trustworthy AI would mean and how corporates should follow these guidelines to well, be compliant with some ethical principles that everyone should agree on at the level of the European Union. Germany also had its own report. Russia also developed its own internal report and national report on AI strategy in relation with the national research centers in Russia. There is the Open AI. Well, first it was an NGO, an association between big corporations, but non-profit one. But since GPT-3, that was basically sold to Microsoft, we can doubt about the non-profit aspect of this organization. But basically, there are a lot of initiatives, either national strategies, ethical guidelines, technical tools being developed like by OpenAI, and conceptual frameworks that are being shared. And this points toward the idea that AI algorithms appear not to be only technical objects. It's not simply like a plane or a television, but they are socio-technological ones. They have strong social impacts and even maybe geopolitical impacts. And this implies that the ethical reflection of artificial intelligence is not merely a technical philosophy, like one on physics, for example, or something. It's more of a technical and political philosophy, because we have social and geopolitical impacts of the choices being made around the regulation, the norms, or the duties we would define for this field of artificial intelligence. So to make things a bit more concrete, I take the example of the European Commission framework for artificial intelligence ethics. They defined a framework for future regulation based on a few pillars here: understanding and transparency of the treatments, their robustness and safety, the non-discrimination, diversity and fairness for data and AI treatments, the importance of human controls and data on AI treatments and the associated responsibilities. The important word here is that of responsibility, privacy and data governance, which are already regulated via GDPR, which is the General Data Protection Regulation in Europe, and environmental and societal impact. So they have a very big guideline book with various criteria to verify for each of these aspects. But we at Quantmetry simplified it for the sake of well, being more pedagogical and more operational when speaking with corporations and people that are indeed in artificial intelligence and have to implement specific and pragmatic measures. So basically, we defined 3 pillars for AI ethics, which correspond to the explainability of data and AI algorithm decisions, non-discrimination with bias analysis and correction, and auditability of data and models. You can always map the EU framework into these 3 pillars. Basically, understanding and transparency go to explainability. Non-discrimination is obvious. Human controls goes to auditability. And we think that privacy, since it's already regulated, does not belong to AI ethics. So it's not a decision whether to comply with regulation or not. You just have to comply with regulation. Whereas ethics is what goes beyond regulation, something for which you have a choice. So privacy is a compliance issue and not an AI ethics issue. And environmental and societal impacts are, of course, ethical concerns to have for artificial intelligence, but we see them as something that is not very practical for the moment. Companies are still struggling with these 3 first very operational aspects of AI ethics. And this environmental and societal impact concern is something that should be addressed in the near future. But for now, we can focus on these 3 pillars of non-discrimination and auditability. So I suggest that maybe you take 10 minutes. I don't know if you know each other so that it would be easy for you to group into 2 or 3 people, or simply take 10 minutes by yourself to reflect on these 3 notions. How would you define explanation of an artificial intelligence algorithm? How would you define and avoid discrimination? And how would you define auditability and of artificial intelligence systems? And then I will ask maybe 2 or 3 persons among you to share their ideas to the audience. If everyone is okay with this, we can start now and in 10 minutes share these ideas from 2 or 3 persons. So is everybody, did everyone understand the instruction and okay?
Hello, sir.
Yes.
Sir, in the question you wrote, we have to define the notion of algorithm, explanation, discrimination, and auditability. What does it mean, sir? Auditability?
Well, basically, it corresponds to this idea of how would you audit an artificial intelligence system? For example, we know about financial auditing, etc. How would you think of auditing an artificial intelligence system?
Okay, okay, sir.
Of course, I will give you the answers to all these pillars, but the idea is to first let you think a bit about them and then explain what are the official definitions and approaches.
Okay, sir.
Okay, we can take 2 more minutes to finish thinking about these notions, and maybe 2 or 3 persons among you can share their thoughts. Okay, great. So are there any spontaneous candidates to share thoughts on these 3 notions?
Well, since nobody wants to answer, I think I'll try to give my opinion.
Great.
So, here are the notions of algorithm explanation. Yes.
Mhm.
So, I think the algorithm should have a clear explanation why it functions this way and not the other way, and what one thing does. Talking about limits of explanation, yeah, I think you're talking about this, like, I think everything should be clear about the algorithm, and there should be no room for mystery. Well, I think so. Maybe there are different fields where mystery should be applied. Well, discrimination, I think. Well, I'm not actually sure what you mean by this, but I think, well, you have shown us the example where 87 people from America
Mm.
were browsing the Google about gun control and got different responses.
Yes.
So this notion means that people should get more or less similar responses without any, well, I know a Russian word, but I don't have a synonym, English synonym. Well, they should get similar and not politically oriented
Mm.
responses. And auditability is like, I think this means that the algorithm can be checked if
Yeah.
if this algorithm really suits the explanation, the written explanation to this algorithm. I think the limits of the audibility should be just the same as for explanation, because these two notions are really connected, as I think.
Okay, great. Thank you very much for sharing your thought. I think you had some very good points on how you thought about these concepts. What we will see is that basically, indeed, explanation is how can we leave the less possible room for mystery in how results are being produced. And we will see that there are different levels of analysis regarding this notion of explanation. Discrimination, as you said, is a possible example is, of course, something that would not be politically oriented, but if this is the use case of the AI algorithm, then fair enough, as long as there is, for example, consent, etc. But at least if we want to, if we have very similar features, then we should, for the individuals, then we should aim for the same results. This would be a possible definition of discrimination. But as we will see, again, there are very subtle definitions of discrimination, and not all are compatible. This is the very important point to have in mind that we will dwell in probably tomorrow. And auditability, which is basically the ability to check the results. Auditability is the basis, is the foundation for explainability and discrimination, and would correspond to a set of processes, procedures, etc., that need to be defined to ensure this ability to explain, to avoid discrimination, etc. And we will see that, again, there are some very strong statements to be made on this notion of auditability. Okay, if there is no other candidate to share some thoughts, I suggest we continue with the presentation. So, I'll just have to smaller. Yes.
I want to share some thoughts. So, firstly, about explanation, I think that we need to make profound testing on various data. So you must not only understand the algorithm, but also know that it works fine on different data.
Very good point. Yeah.
Yeah. So next problem is that the limit of explanation, that if the information about algorithm is public, it can be harmful, because some bad people can use this as a weakness to make some cyber attack, or so this is the problem. And if we move toward the general AI, the problem will be much worse, because such powerful technology can be very harmful in bad hands. So about discrimination, I think that there are some really hard points. For example, some people prefer simple content. No, you can scroll YouTube videos, and if you like simple videos, YouTube will tend to show you simple videos. But the problem is that we can think about this as discrimination, because it decides for you that you should watch simple videos. So it's like loop, positive loop, and maybe it's better that there must be like some balance between what you prefer, and what you must see, but it will be new for you. So you need to see some new content, and you can see some preferred content. But if you see only preferred content, it's like information bubble, and it's very bad. And the auditability, I think the problem with auditability maybe in one thing that if the audition is made inside of the company, like you can face the problem. For example, Google is making audition of Google, and so yeah, they can do some bad things and nobody will know because they make audition of themselves. So we need to make some outer system of control for such companies. Like, I don't know, maybe it must be a government organization or something. So that's all.
Yeah, you made some very good points here. This is a very exact regarding discrimination. There is a very good and important question about, yeah, it's okay to use algorithm, but basically, what is the metric you are trying to optimize? And often what YouTube or other platforms are trying to optimize is time spent on the platform. It's not the spiritual or intellectual growth of their users. So if they think that pushing to you preferred content will make you spend more time on the platform, this is the metric they will be optimizing. And this is discriminatory on another level, which is how do we share knowledge between individuals, etc. And of course, auditability, one of the very good points is that who are the authorities that are going to audit and how are we going to train them? Because even the public authorities today have very little training and understanding of how artificial intelligence works. How can we frame auditing for corporates, etc. And this is a very important problem for next years to be solved. Yeah, I think Luke raised his hand, his virtual hand. So Luke, if you want to speak, do not hesitate. Otherwise, maybe it was just a mistake.
I think one person wants to speak up.
Yeah, I saw someone raising hand. It
Yes.
was Luke, but I am not listening here.
Yeah, so Luke, if you want to say something, please do it.
Hello, sir. May I try, sir?
Hello.
Hello.
Yes.
Can you hear me, sir?
Yeah, I can hear you. Yeah.
Okay, sir, as per my understanding about algorithm explanation is we have plenty of machine learning algorithm as you shown, like k-means algorithm or regression algorithm. Algorithm should be chosen according to the data set available, and that should give the best result out of the historical data. And discrimination means whenever we choose an algorithm for finding out a result, we should not miss a particular data available in the given data set. For example, if we take the data set as COVID-19, let's say if our machine learning algorithm should predict the person, whether it is on the behalf of historical data of the patient. For example, patient having a breathing pattern, or historical data says, let's say if he have a traveling history, and machine learning algorithm should decide whether it is COVID positive or he is a healthy patient. But in the historical data, if some values are that if a patient having no such kind of historical data, or he not having travel history, and even that he is a COVID positive, that means that value should not be discriminated. That's values, even it is a less number of patients who are not having historical data, who are not having breathing patterns, also he is a COVID positive, that values also should be taken into consideration. And auditability, as per my understanding, means out of these many machine algorithm, we should audit which algorithm should give the best result out of the given historical data. And if we have a unseen data, if a person is coming on the behalf of the historical data with the unseen person behavior pattern, if we are able to give result, whether he is a healthy patient or he is having COVID positive, that should be auditable depending upon the machine learning algorithm. This was my understanding, sir.
Thank you very much. Yeah, this was a very good idea about representativeness of data is very important to ensure non-discrimination, because as you said, if you have some people who are not represented in historical data, you will probably make random decisions for them, or at least a well-managed decision for these subgroups. So here you have a problem of discrimination for these subgroups. And of course, representativity of data is something that should be auditable because it is at the basis of well-trained algorithm and good behavior in new contexts. So the ways one can audit this are very important aspects of this auditability problem. Okay, well, thank you very much all for sharing your thoughts on this point. So the idea now is to dwell in the rest of the course today and tomorrow on these three pillars of AI ethics. What do they mean exactly? What are the subtleties you need to have in mind? And what are the potential solutions to implement good explanation procedures, non-discrimination, or auditability? And of course, what are the limits we are nowadays facing for these three ideas?
Sorry, can I interrupt you for a moment?
Yeah,
so Luke has some problems with his microphone, so he sent his question, and he wanted to ask about the role of bias in data itself.
Mm-hmm.
For instance, blacks are more likely to be shot in America,
mm-hmm.
and that has nothing to do with any algorithm, but the data, the source data that everyone has.
Mm-hmm. Yeah, exactly. This is when analyzing the sources of bias. We'll speak about it probably tomorrow, but in very short summary is that you have different sources of bias. You have the data bias as the one you mentioned, but this data itself is generated from real world. If you have bias in the real world, which is, as you said, for example, there is a bias that black people get more shot than white people in the US, well, data will only reflect this real world situation. So you have real world bias, you have data bias, which is supposed to reproduce the real world bias, but not systematically. You must have some bias that is very specific to data you collected. So you generate a new type of bias. Then you have the algorithm bias. The situation of underfitting, for example, I mentioned, can correspond to a notion of algorithmic bias because it has the bias of a linear relation. And even if your real world relations are not linear, the algorithm will have a bias of linear relation. And then, of course, you have the bias of users of the output of the model. You can have, for example, a model that targets people according to their skin color. But if you use this model to send, for example, skin care that is adapted to skin color, this would be okay. But if you send insults according to the skin color of the person, this would be a bias and racist use of the algorithm. So you see that you can introduce bias at very different levels of the process of reality, data collection, algorithm, and use of the algorithm output. But yeah, very good point. Part of the bias certainly sometimes come from reality itself. And our aim is to not build, because what artificial intelligence does is automate decisions. So if you have a bias that is very localized in reality, but then you use artificial intelligence to automate decisions and scale them, then you will reproduce this bias everywhere. And the problems you will generate will be much, much heavier than the initial problems you had. So it is very important to have in mind that even though you have some bias in reality, you must do your best to build an algorithm that corrects this bias. And the problem is, who decides how we correct these biases? What are the techniques to do so, etc. So this is the type of questions we will need to address. We will not, of course, be able to address all of this in a 3.5 hours course, but at least you will have the basic concepts to think about these problems and some references. So if we think about these three concepts, explainability, discrimination, and auditability, we might think these concepts can be used and thought of about classical procedures. What is so new about machine learning or artificial intelligence that we need to have a specific reflection and a set of tools, etc., to deal with these new types of algorithms. Indeed, surveillance, automatic decision-making, discrimination, opacity, etc., all these are old words and an old battle against bureaucracy and classical procedures that is being renewed against machine learning. So one might think, is there really something new under the sun regarding artificial intelligence? And what we will see is that there is something new regarding artificial intelligence and machine learning if we think about these three concepts. And the way we will point out what is so new about machine learning is by analyzing the historical connection between classical procedures, such as bureaucratic systems. And here the notion of bureaucratic system is not pejorative at all. It's a simple definition of a set of rules, an administrative order that applies a predefined set of rules. This is what we mean by a bureaucratic system. And this historical connection between these classical procedures as exemplified by bureaucratic systems and machine learning will help us shed light on what is really specific and new in the challenge that machine learning poses to explainability, discrimination, or auditability. So this is our next part. So basically, bureaucracy, we will think of it as a paradigm for classical computer procedures. And by classical computer procedures, I mean all algorithms besides machine learning and artificial intelligence ones. So bureaucracy, if we think of it historically, was a professional body of scribes who uses a technique, mainly the ability to write, as a modality of exercise in power. So by writing, they are able to perform computations for the entry of taxes and for the management of the army. So here we see that there is a strong connection between this notion of exercise of power and technology that allows traceability. And through this traceability, the centralization of central control. So this connection is at the heart of what a bureaucratic system does and what a set of classical procedures is supposed to be performing. Then we will think about another historical definition or conception of a bureaucratic system by Max Weber, which is a German sociologist of the 19th century, that analyzed the parallel between what he called the production order, which is the machines during the Industrial Revolution, and the administrative order, which corresponds to a bureaucracy. And what he saw and analyzed was that both had this tendency to standardization and depersonalization. The goal of the production order and the Industrial Revolution is to eliminate the artisan bias, the way his hand makes objects, etc. We standardize objects, we standardize machines that produce these objects, and we standardize their characteristics. And of course, we depersonalize these objects. There is no fabricant or craftsmanship artifact. It's completely depersonalized. And you can see that, for example, workers in factories are supposed to be interchangeable because the procedures are defined and they simply have a set of actions to perform in order to make this new object in the production order. So here, artifacts or decisions, if we think about the administrative order, basically we have a set of procedures to produce decisions, are not biased according to this idea of standardization and depersonalization by the executants, either the administrative order agents or the production order workers. And of course, these agents are interchangeable. The agent that is rendering the decision or the agent that is producing an object, they are supposed to be interchangeable since we define some standards for the decision-making procedure or the object-making procedure. But of course, there is not a complete depersonalization. You still have the designer bias. either the person that designed the administrative order, the laws of the bureaucratic systems, etc., or the engineers that made the system and that the workers are fabricating inside factories. So he really pointed out this very common characteristic between the production and the administrative order. And another one, which is quite impressive, because at that time there was no computers or even the idea of a modern computer. He saw that both have a tendency to optimize and increase performance. This is the goal of the Industrial Revolution, to make more objects more quickly and scale. But this is also the goal of an administrative order: produce more decisions on a bigger scale and more quickly. And the second thing he pointed out is the deep tendency of both to automation. And this is very impressive in the sense that during the Industrial Revolution, of course, one can think that automation was present through the way we were leading the energy revolution with the heat, etc. But for the administrative order, it's very strongly, this automation is very strongly related to an idea of computation, automating computation, automating decisions. And he saw that both have this tendency to automation. Machines and the production order tend to automate the order of objects production, and the administrative order has a deep tendency to automate decision production. And by automation, you need to produce machines to automate this. And one can see that this strong historical connection that Max Weber saw indeed appeared during the 20th century. If you look at organization theories such as Taylorism, they confirm the reflection of Weber on the tendency of to automation and optimization of human labor, because basically these are theories of how can we automate the tasks that are being performed by humans to make either new objects or make new decisions at the company or factory level. And these concepts of organization theory, which were inspired from Max Weber, they themselves deeply impacted the rise of computer science as a discipline. For example, the notions of program, the notions of procedure, the notions of diagrammatic representation that are very used in computer science, they all stem from management theories. The first ones to invent these notions were people that did research in organization theory. And von Neumann himself, which is one of the founding fathers of computer science, defines a computer program as a series of precise computation tasks that humans would take centuries to execute. So here again, the way they thought about computer science is an automation of tasks humans have to perform. So here we see that if we think about classical computer procedures, there is a strong connection with bureaucratic systems and automation of decision procedures. And conversely, if you think about nowadays bureaucratic procedures, they are more and more computerized. So we led a survey with Etalab, which is a French government agency in charge of data and algorithm, and we asked them what are the types of algorithms used to automate the bureaucratic procedures of the French state. And there are three main types that are historically used. Basically, computation algorithms to compute taxes, to compute welfare or subsidies. You have decision trees to help make some decisions, and you have matching algorithms, for example, algorithms that will match students with positions in universities. And only very recently did they start using machine learning in new use cases where they need predictive policies through detection of some weak signals. So we see here that it is very natural that most of the tasks that need to be performed by the bureaucratic system of the French state are mapped to algorithms that will perform some computations and give some outputs for the citizens or the agents in charge of the bureaucratic procedures. So here we see how we had an evolution of these bureaucratic procedures, from old bureaucracy to modern bureaucracy, which can be mapped as an administrative order with the production order, with this deep tendency to automation, etc. And once we had this ability to automate computations and decisions, well, bureaucracy naturally tended to use computer science and programs to produce new decisions. So what is problematic with adding machine learning to producing decisions in bureaucratic systems, either public ones like the state bureaucracy or private ones like corporate bureaucracy? Well, to analyze what would be problematic, we first have to think about what's the difference between machine learning and classical procedural thinking. And generally, when you look at reflections on how machine learning is a rupture from classical programming, there is a set of ideas that you will hear often. For example, that the mode of generation of software is different. Artificial intelligence based on machine learning are trained, they are not programmed, which is somehow true, because as I said, if you want to build an autonomous driving system, you do not program explicitly all the possible scenarios and situations that the car will have to deal with, because simply it's impossible to deal with all possible situations of pedestrians, of car movements, of red, green, orange lights, etc., all combined. What you do is simply try to capture as much different situations as possible through data with videos, and then train an artificial algorithm to recognize what is the best decision according to the situation we are in. The second point is that the nature of software corresponds to non-procedural programming. Basically, you will use machine learning precisely when classical decision theory is no longer applicable, because you have too much data to take into account, or your data is too abstract to be mapped to a way we humans can think about in the sequential decision-making procedure, etc. So it is precisely when it is very complex to establish a classical decision procedure that you will use machine learning. A third point is about explainability and auditability. As I said earlier in the session, here we are focusing on machine learning. But basically, when you use machine learning, well, you are writing a piece of software that has an internal representation of knowledge from the data you use to train it. This is very different from the other type of artificial intelligence, which is symbolic AI, expert systems, which have a very explicit representation of knowledge. Of course, the software you write from an expert system might be very complex, very long, but in all situations is simply a set of rules. Complex set of rules, but still a set of rules that is explicit and can be understood by a human. But if I give you a deep learning algorithm, you can look at it and look at the program, but you cannot see how the knowledge is being encoded in the algorithm. You only see a set of parameter optimization, data transformations, etc. And this is a very abstract representation of the knowledge that was present in the data. This knowledge is now represented as the parameters of the model, but it's very abstract representation. It's an eternal representation of the knowledge. And the fourth point is that because of this new way of making decisions, we are now starting to have a divergence. Until now, computerization and proceduralization went hand in hand. Basically, if you wanted to automate procedures, you basically turn them into computer science programs. And if we had new types of programs, basically they would correspond to classical new procedures. But what machine learning does is that it deepens, of course, computerization, because machine learning is simply new types of computer science programs, but it does not deepen the classical notion of proceduralization. It introduces new modes of decision and action. And this is what might be problematic in the situation of bureaucratic systems that would rely on machine learning algorithm instead of classical, easily explainable, with explicit representations types of procedures. So the question now is, what is so problematic about machine learning new modes of decision? Because the common intuition about AI systems is that, well, they might pose a problem in decision making. They can generate decisions or discrimination that are difficult to understand, etc. But before analyzing this, we need to really take into account major ambiguities regarding the three concepts we defined, or at least we pointed at. For example, regarding explainability, Is the explainability, the interpretability problem for scientists building AI systems? So is it an expert problem? Does an expert really understand the details of the algorithm he built? Or is it the pedagogical problem of explanation to non-expert users and decision makers or ordinary citizens? And sometimes you see this confusion even at the legal level. For example, the GDPR, the European regulation of personal data used by algorithm, you sense that sometimes they are speaking about explainability in the sense of expert interpretability, and sometimes they use explainability in the sense of pedagogical explanation to non-expert users. And the confusion between the two led some people to say that, well, since we need to have an explanation to non-expert users, then you need to find some very pedagogical ways to explain how deep learning works. So is this really the issue about explainability? We'll see that probably not. Regarding discrimination, how should we define a fair algorithm? Is it an algorithm that does not use the skin color as a decision variable? Or is it one that can use this variable but ensures that we have homogeneous decisions for groups with different skin colors? Because if you want to ensure this homogeneous decision, you need to at least have collected this data about skin color to measure the impacts of your decision. If you don't have this information, you will not be able to ensure that you have homogeneous decisions according to skin color variable, and hence you might generate discrimination. And again, there's a lot of confusion between what is the correct way to address non-discrimination. A lot of people, for example, in France, think that we should not collect sensitive data such as skin color or sexual orientation or political orientation in surveys. And until today, most surveys do not use this data. But if you want to ensure good non-discriminatory decisions, we will see that you would probably need this data to be collected. And finally, regarding auditability, is a program auditable if we simply have access to source code, or if we have access to outputs or a specific set of tests? For example, again, I take an example I know of here in France. There was a problem with the algorithm that matched students with positions in universities. And when they asked for transparency and auditability of the system, they simply outsourced the code. But this is clearly irrelevant and insufficient in the sense that if you don't have the data that's led to the rules, explicit rules or learned rules used to produce the decisions, then the code itself is not sufficient for good auditability. And as we will see, even if you provide the data that served for the training of the algorithm, you probably have not enough processes for auditability. Auditability is much larger and much broader concept that needs to be understood and addressed. So now we will focus on each of these concepts, and probably for today we will only get to deal with explainability and discrimination and auditability for tomorrow. So first part is to understand why we care about explanation. There is this ideal of government transparency. Here again, government in the very broad sense of public government, but also private government, like in corporations, etc. So if we have this ideal of transparency, then we can map it to a right to an explanation of the decisions if we are using bureaucratic procedures. And the way this is translated in most positive and concrete law systems is that citizens or users have the right to understand the reasons of the decisions affecting them. This right to an explanation is a fundamental ideal for several reasons, because it gives you a way to appeal from a decision, because since you have the right to an explanation, then the decision being made needs to be explained, the criteria need to be given, the data used need to be given, and of course then you can appeal from a decision if you see that faulty data or reasoning was used, or if there was a dubious application of legal principles, etc., etc. So it's very important as a principle to allow appeal from a decision. And also it's very important because it allows and gives the opportunity to develop awareness of rights and interests and establish strategies to defend them. Because if you are facing a completely opaque bureaucratic system, then you do not understand decisions, and you do not even understand how you can evolve or do things differently to better defend your interests, since there is no possible strategy in face of a completely opaque system. But this is from the point of view the benefits for citizens, but of course it is a great source of benefits for the government itself, because explanations act as a channel for incentives. If I have completely opaque procedures, I do not know how to act to conform other than just blindly obeying. But if I have a good explanation, then I know what are my interests, and in order to match my interests, I can adapt my strategy and match the procedure defined by the government. So a simple example, for example, is taxes. If you have a completely opaque tax system, then you simply pay your taxes, but there is no incentive to, it's not an incentive channel to control the behavior of citizens by the government. Whereas if you have a transparent tax system, you can use this as an incentive to control behavior. For example, if you want to push a more ecological behavior, then you can tax a behavior that generates more CO2 and help through, for example, credits, etc., behavior that is more green or environment friendly. And so by being very clear and explicit about how you tax things or you de-tax other things, people will understand what is the best strategy for them to optimize their interest, and they will probably start having a more green friendly and environment friendly behavior, simply to optimize their financial interests, which correspond to paying less taxes. So there is no systematic opposition between respect of citizen rights and government efficiency. And now the question is, can we use machine learning and maintain explainability for every user with no degradation and possibly improvement of government transparency? So if the answer to this question is yes, then machine learning is probably not a threat and could be scaled. But if the answer is no, then we should think twice about scaling bureaucratic decisions using machine learning, because then you could lose this point of ability to appeal from a decision, because people would not be able to understand decisions. We would lose this ability to develop strategies to defend one's own interest, and hence lose this incentive channel the government has at its disposal. So now, first conceptual, very important point is the distinction between explainability of the procedure and explainability of the output. Fundamentally, you need to, the fundamental distinction of made between these two relies on the idea that you do not always need an explanation of the procedure to explain a decision. So for example, if you are applying, and here we think about any procedure, right, either based on machine learning or not. If I think about a system like a social security system that defines who has right to subsidies, etc. If I ask for an explanation of why I did not get a certain subsidy, what I expect is a very simple explanation of the decision that concerns me. For example, you did not have right to this subsidy because your revenue is too high, or because you are above the legal age for this subsidy, etc., etc. But I'm not expecting an explanation of the procedure of the social security system. I'm not expecting a course of how the laws of the social security system were made, or why they used such or such criteria. I only need an explanation of the decision that affects me. And this distinction is very important because, again, there is a lot of confusion in a lot of people's mind between these two concepts. And basically, what we will see is that in most situations, what users of systems based on artificial intelligence or not ask for is explanations of outputs, explanations of decisions. They do not care at all about explanations of procedures. So if you use artificial intelligence and produce a decision, you need to explain the output, but we certainly do not need to have a pedagogical explanation of how deep learning works in order to ensure this explainability criterion. So now if we focus on classical bureaucratic procedures from the explainability point of view, you can see that bureaucratic procedures can generally easily be turned into explainable programs because they correspond to a set of rules, and rules can easily be turned into explainable programs. But another very specific property that classical bureaucratic procedures have is what the so-called explainability by excerpts. It's the example I gave. If I do not have a social aid, I can have an excerpt, a very small explanation, which is your revenue is too high. I do not have an explanation that that refers to all the criteria. For example, yes, you are a European citizen. Yes, you are above 16. Yes, you are married, but your revenue is too high. The explanation goes very exactly to the excerpt that is relevant for me. And this property is very important to have in mind because classical bureaucratic procedures were built to ensure this property. And agents that are using these bureaucratic procedures were trained to give these explanations very quickly. They are very able to give the explanation by excerpts very easily. So these two properties that are properties of these bureaucratic procedures and that agents are very aware of and trained to use are critical to the massive use of classical bureaucratic procedures as decision aid. And this is why our societies were able to scale massive states, were able to scale massive corporations, international corporations, etc. Because we are able to define classical procedures which are translated into explainable sets of rules and programs, and we are able to explain outputs by simply referring to excerpts that allow to explain this specific decision. We do not refer to the whole procedure for an explanation. And this is very important because not all of artificial intelligence has this property. And this is what's so problematic with machine learning. So we ask the question, is there really a new problem with machine learning? Here you have the answer. Yes, we have this problem because we cannot ensure explainability by excerpts like for classical procedures. Then we can think about the simplicity criterion. So as I said, we have this ability to go to an excerpt. So I explained how decision tree, for example, or any artificial intelligence algorithm basically works. It's data space segmentation, for example. Can we map this simplicity, the ability to have an excerpt very quickly, as some criterion on data space dimension reduction? Basically the answer is no, in the sense that there is no way to formalize simplicity of explanation for a developer. You can always choose a subset of your data space and use it for an explanation, but there is no automatic way to formalize this. So this is what's so problematic about this notion. It's a very intuitive notion. It's a very contextual notion, but once you try to map it into a very specific definition for machine learning, it's very hard to do so. But again, we should not generalize too quickly. Not all machine learning algorithms are equal. If you think about the decision tree, well, if you ask me, this is very explainable. You have the graphical interpretation to the left, then you have the data space segmentation that corresponds to this graphical representation to the right, and we can easily explain both the procedure and the decisions. The procedure is, as I explained earlier, basically I'm looking for a way to segment the space by minimizing inhomogeneity inside my boxes. And this is how the algorithm works and draws all the frontiers inside the data space. So this is the procedure. And if I have a decision that I want to explain, for example, why is my prediction, for example, has value 15 degree for a new data point? Well, the simple explanation would be simply referring to the graphical, to the graphics here and saying, well, we noticed historically that data points have, for which the wind speed is above 60 kilometers per hour, have an average temperature of 15 degrees. And it's a receivable explanation. So here, with a decision tree which corresponds to a machine learning algorithm, explainability of the procedure and explainability of a decision do not pose any problem. But this is not guaranteed for all types of algorithms, as we will see now. If we take the exact same example, but think about 3 types of algorithm. As I said, for decision trees, we have a clear data space segmentation criterion, and we can very easily map a new observation to a decision and explain the decision. But now if we move to the so-called parametric models, ones that will use powers and square roots, etc., of the variables, of course, they will probably, again, segment my data space. But now the dimensions of the data space are not so easily interpretable. Here, for example, we have the cube of the speed divided by the humidity, and you have the squared of the humidity plus the square root of the speed of the wind. But since we're dealing with a physics example, you can think, well, even if I have complex dimensions like this, it's not so problematic because I understand that physical phenomena can use more complex mathematical equations. But imagine I was using this model to predict, for example, something, and the variables correspond to height of a person and its weight. If I give explanations that use as dimensions the square root of the height plus the square of the volume, etc., of an individual, this would mean nothing to you. Even if we have a clear data space segmentation in these dimensions, they have no explicit meaning, especially if you use them on use cases like credit score granting, etc. But this is an intermediate situation because at least you have formal dimensions for your space, even if it's complex equations, and you are able to draw frontiers in this space that can be formalized through inequalities, etc. And there is a last type of algorithm, for example, deep learning. If I look at an intermediate layer of a deep learning algorithm, I don't even know what are the dimensions of the space, because you have a set of nonlinear transformations of your input data, and you have no interpretation in terms of dimensions of these intermediate layers. And so even first, you don't have these dimensions, and you do not have the exact inequalities that will allow you to draw these frontiers on the data space. So we are completely blind regarding these intermediate layers of deep learning. We do not understand the data space dimensions, and we are not able to formalize what are the frontiers, are the segmentations that are being drawn by the algorithm inside this space. So here's an example. I don't know if you're familiar a bit with how a deep learning algorithm works, but basically it just corresponds to a set of neurons that you are seeing here that correspond to these data points, green, blue, and red. We colored the input layer, the so-called input layer, in green, the output layer in red, and what the so-called intermediate layers in blue. So what is the input to a deep learning algorithm? You simply take an image. So here we have a 28 by 28 pixels image. So 28 here and 28 here. And you have a level of gray, for example, between 0 and 226. And each pixel will have a level of gray. And then you will map this image to a 28 by 28 is 784. You will map this to 784 neurons. You will have then 1 neuron per pixel, and the input value to the neuron will correspond to the level of gray of the pixel. So until now, it's very simple. And then you have the output layer, which will correspond to 10 neurons, and each neuron, the first neuron will correspond to figure 0, the second neuron will correspond to the number 1, and the last neuron will correspond to number 9. What you are asking here for the model is that I want the neuron number, the first neuron to fire if I have an image of number 0 here. And I want the second neuron to fire if I have an image of 1. And I want the last neuron to fire if I have number 9 in the image. What I mean by fire in the last layer is simply the neuron should have the highest value. So the first neuron has the highest value if there is a number 0 here, and the last neuron here has the highest value if I have a number 9 here. So how can we achieve this? Well, basically you feed, it's a supervised problem. You just feed the model a set of images with numbers in them and pixels with levels of gray. This will feed the input layer. And since it's supervised, you know, in your training set, you have the label, which is basically, well, for this image, we know that we have a number 7. You use this number as a label, and then you ask the model to optimize the so-called weights. Basically, the links here will correspond to weights. I do not want to get too technical, but basically you simply perform a weighted sum from all the previous neurons to have the value here, and plus a nonlinear transformation. So you do a value here multiplied by value here, a value of the array multiplied by value of neuron. You sum all of them, you operate a nonlinear transformation, and you get the value for the next neuron. So it's a bit complex, but I invite you to look at an example on the internet. You see that it's very easy. But the important point here is that we understand what are the dimensions of the input space. It simply corresponds to the level of gray of each of the 784 pixels of the image. We understand what are the dimensions of the output space. It's the natural numbers space from 0 to 9. But no one understands what's going on in the intermediate layers. We do not have any intuition of the dimensions, and we have no idea of what are the segmentations that are operated by this algorithm. So here you see that explainability of outputs is not always guaranteed, even if you use local approximations. And again, there is no guarantee of explainability by excerpts. If I ask you, why are you predicting here value 7? You are not really able to give a good explanation, let alone an explanation by excerpts. You can maybe explain the procedure, how the neuron number 6 fired, and that this is the highest value, and that this highest value was computed by performing nonlinear transformations and sums, etc. But here you're just explaining the procedure. You're not giving a very specific and excerpt for the explanation. And this is exactly why AI, for some use cases, might face massive adoption issues, because, well, if you are not able to give easy explanations for such use cases, then we'll probably have a lot of problems subsequently. So how can we achieve a formal approach to explanation? Here we just saw that we might have a problem with some types of algorithms like deep learning, but we might not have a problem with other types like decision trees. How can we achieve a formal explanation to this, a formal approach to this notion of explanation, so that we are agnostic of the model being used? So you need to make some conjectures. First one is a sociological conjecture on the demand. As I said, most requests for explanations are requests for explanations of decisions, of outputs. People are not asking for an explanation of deep learning. And a second conjecture on supply, the fact that we are able to give explanations of outputs by focusing only on inputs and outputs. We do not care about the intrinsic workings of the algorithm. So basically, this conjecture means that we can consider the model as a black box and simply focus on inputs and outputs. So basically, there is a very famous framework that can be used that simply formalizes this intuition. Basically, here you have the inputs data, which we can use to produce the explanation. We have the output, which corresponds to the decision. We consider that the model is completely a black box. We do not look into the inside of it. We do not care of how it works. We do not care if it's a decision tree or a deep learning algorithm, etc. And the question we are now asking is, if we are in this formal framework, what is the type of explanation that we are able to produce? And what is interesting is that you have three properties of explanation that you can have, even if you consider the model as a black box, and that correspond to maybe 90% of situations where people will ask you for explanations. So by using only inputs and outputs, you can identify the factors of a decision and their values, because since I have here for example, the sex of the individual, its age, its revenue, etc., that were used to grant him a credit or not, even if I don't know what model is being used, I can understand what are the factors of the decision, and even sometimes understand the magnitude of their impact and the relative order in the decision. And of course, I can also understand if there was any use of protected variables or proxies as input. So this is the first important property of this framework, the black box framework of explanations. The second important property is that it allows us to check consistency between decisions. Again, even if I don't know what model is being used, I simply look at outputs and I look at inputs. If I have very similar inputs but very divergent outputs, then there is inconsistency in the decisions. And I can, for example, either appeal from the decision or ask for more explanations. I can also detect threshold effects. For example, if we see that minor changes in inputs lead to major changes in output, we can think, is this a legitimate decision-making procedure, or is there a problem here that needs to be corrected? So again, consistency between decisions and analysis of threshold effects is possible using a very simple framework of explanation where you don't care about the inner workings of the model and just about inputs and outputs. And finally, it allows for counterfactual reasoning, which is a very important point if you want to adapt your strategy to in face of a decision system. I can change the inputs to see how the outputs are changing. And this is enough for me to do counterfactual reasoning, such as, well, if my revenue was 5K higher, then I could have had the credit granted. But if my revenue was lower by 3K, for example, I'm not sure they would have had the credit granted. So basically, I can explore scenarios and see how the outputs would have changed. So here, this gives us a framework, a potential framework for analyzing explanations. And I suggest that we take maybe the 4 last minutes to take any questions if you have some, and leave the rest for tomorrow. We will finish this part about the explanation framework, how we can use it, what are its limits, etc., and then speak about discrimination and auditability.